What is kinetic theory? Kinetic theory is a particle model that explains the behavior of gases by describing them as tiny particles in constant motion. Temperature measures how fast the particles move, and pressure comes from collisions with the container walls. So here is the big picture. We've previously talked about the ideal gas law, which connects macroscopic variables such as pressure and volume and temperature and the amount of gas without referencing molecules. The ideal gas law states that PV is equal to nRT. The kinetic theory is a model that provides a microscopic foundation and explains why gases behave the way that they do. To understand kinetic theory, we need to understand the assumptions made by this model. First, that gas particles are in constant random motion. And second, that the collisions between the particles and with the container walls are perfectly elastic. That means that the kinetic energy is conserved. Third, the particle volume is negligible compared to container volume, and that there are no intermolecular forces except during collisions. The kinetic theory helps us to understand temperature from a molecular standpoint. It states that the temperature is proportional to the average kinetic energy of gas particles. We can write this equation in two ways, depending on whether you're using Kb for Boltzmann's constant or you want to write it in terms of R, the universal gas constant. So the first way is to state that the average kinetic energy is equal to 3/2 times the Boltzmann's constant times the temperature. The second way is to say that the average kinetic energy is equal to 3/2 times R divided by Avogadro's constant times the temperature. Both of these equations are equivalent because for a mole of gas, the universal gas constant is equal to the Avogadro's constant times the Boltzmann's constant. Not all particles move at the same speed. So the Maxwell-Boltzmann distribution shows how particle speeds are spread out at a given temperature. So for temperature T1, there are some particles that are slower and some particles that are faster. You'll notice that there is this peak right here, and this is called the most probable speed. Shifted a little bit to the right is what's called the root mean square, which I will show you how to calculate in just a little bit. The reason it's shifted a little bit to the right is because you'll notice that this curve right here is asymmetrical. And if you have a higher temperature, so T2 has a higher temperature, you'll notice that the curve spreads out more, and you'll notice that the peak shifts to a higher speed. Next, we're going to take a look at the root mean squared speed. So how do we calculate the speed of a particle? So the way we do that is to use the average kinetic energy equation that was set to 3/2 times the Boltzmann's constant times temperature. We set that equal to the equation for kinetic energy that we learned from first semester of physics, 1/2 mv squared. And then we solve for v. And if we solve for v, we find that v is equal to the square root of 3 times the Boltzmann's constant times the temperature divided by the mass. Now, m is the mass of the particle, and you'll notice that as m decreases, the speed increases, and vice versa. So they're kind of inversely related there. And so lighter molecules will move faster than heavier ones at the same temperature. Kinetic theory also helps us to understand pressure. Gas atoms are constantly moving and colliding with each other and with the container walls. Each collision with a wall exerts a force. Pressure is the force per unit area due to the sum of all collisions. Pressure is defined as the ratio of the perpendicular force exerted by collisions to the surface area. Here's the equation for pressure, where F is the total force of particle collisions on area A. Collisions conserve momentum and can be analyzed using conservation of momentum. Pressure exists throughout the gas, not just at the boundary. So even though we measure pressure using a container wall or boundary, inside the container, we still do have pressure. All right, let's take a look at some sample problems here. An ideal gas is made up of n diatomic molecules, each of mass m. All of the following statements about this gas are true except A, the temperature of the gas is proportional to the average translational kinetic energy of the molecules. That is true. B, all of the molecules have the same speed. That's not true, as we saw in the Maxwell distribution curve chart. C, the molecules make elastic collisions with each other and with the walls of the container. That's true. And D, the average number of collisions per unit time that the molecules make with the walls of the container depends on the temperature of the gas. And that is true. If the average kinetic energy of the molecules in an ideal gas at a temperature of 300 K is E, the average kinetic energy at a temperature of 600 K is what? So we're going to use our kinetic energy equation. And from this equation, you'll notice that the kinetic energy is directly proportional to the temperature. This means that if you were to double the temperature, you would double the kinetic energy. So the temperature initially was 300 and now it's 600, so that's double. So double the temperature will lead to double the kinetic energy. So the answer will be C. An ideal gas is enclosed in a container. The volume of the container is reduced to half the original volume at constant temperature. According to kinetic theory, what is the best explanation for the increase in pressure created by the gas? Okay, so because the temperature is constant, that means that the average speed is going to be constant as well. So let's take a look at our options. The average speed of the gas particles decreases, but they hit the container walls more frequently. Okay, so the problem here is that the average speed of the gas particle decreases. So it's not going to be A. The average speed of the gas particles is unchanged. Okay, that is true because the temperature is constant, but they hit the container walls more frequently. And that makes sense because now we have the volume, which is half of what it was before. And so it's got a smaller volume inside. And so there's going to be more collisions. So B makes sense. Let's take a look at C. The average speed of the gas particles increases, and that can't be true. And then D, the average speed of the gas particle increases. So that can't be true. So the answer is going to be B. Hydrogen gas and oxygen gas are in thermal equilibrium. How does the average speed of the hydrogen molecules compare to the average speed of the oxygen molecules? We're going to start with our average speed equation. Notice that the average speed is proportional to the square root of 1 over m. Now we want to connect the mass of one molecule to the molar mass. And to do that, make that connection, we're going to say that the mass of one molecule is equal to the molar mass divided by Avogadro's number. And we're comparing the average speed of one hydrogen molecule to the average speed of one oxygen molecule. And we know that the average speed is proportional to the square root of 1 over m. And then now we're going to substitute the molar mass over Avogadro's number for the mass of one molecule. Because this is in the denominator, I'm going to flip this, and so it's going to look like this. Now notice that the Avogadro's numbers will cancel out, and that leaves us with a square root of 1 over the molar mass of H2 divided by square root of 1 over the molar mass of O2. Now notice that we have two fractions, one on the top of the fraction and then another fraction on the bottom. So I'm going to take the inverse of the bottom and multiply by the top, and that gives us the following. All right, and then substituting the numbers over here, we get the square root of 32 divided by 2. And this 32 divided by 2 is 16, so square root of 16, and we get 4. So the answer will be 4 times greater. A sample of gas is in a tank of constant volume. The sample absorbs heat energy so that its temperature changes from 300 Kelvin to 600 Kelvin. And V1 is the average speed of the gas molecules before heating, and V2 is their average speed after heating. What is the ratio V2 to V1? So we're going to start with our root mean squared speed equation. From this equation, you can see that the average speed is proportional to the square root of the temperature. Now we're comparing the speed, the average speed at V2 to V1. V2 is the final speed, V1 is initial speed, and we know that the velocity is proportional to the square root of the temperature. And we're going to substitute the final temperature for T2, which is 600. T1 is the initial temperature, which is 300. So 600 divided by 300, we get 2 and square root of 2. So the answer is going to be C. If you found this video helpful, check out my next video on thermal energy transfer and equilibrium.